So it's a great pleasure to have here Adriana Romero-Soriano. I have some your bibliography because I want to introduce you properly. So Adriana is currently a research scientist at Meta AI Fair, adjunct professor at McGill University, our industry member of Mila, and a Canada CIFAR Chair. So her research is about problems that require inferring full observation from limited sensory data, building models of the world with the goal to improve impactful downstream application responsibly. Her most recent research focusing on improving the quality, consistency, and the representation diversity of visual content creation systems. Adriana received her Ph.D. from University of Barcelona, and I think we met the first time there. I was finishing my PhD and we were starting. And her advisor was Dr. Carlo Gatta. And after that, she spent 2 years as a postdoc at Mila, working with Bengio. So thank you for coming for this talk, and we are here to listen to you.
I think we're starting with a question.
But this is more. Yeah. Sorry, our settings are a bit improvised.
So thanks for the introduction. It's a pleasure for me to be giving this talk here today. So the topic of the talk will be generative models as queryable world models. Okay. There's a bit of delay, I guess. So let me start with this little introduction. So far what we've seen over the past few years is a lot of progress in training representation learning models, and this progress has come in a big part due to the large-scale datasets that have been used to train representation learning models, or sometimes called foundational models. So these models have been trained on really huge datasets that are scraped from the internet. However, over the past couple of years or so, we've also seen a lot of progress in content creation models, in particular imaginative models, but also large language models. And so what we envision moving forward is that we'll be moving away from training machine learning models in general with static data sets. And one possible alternative to that would be if we have access to a good generative model that is representative of the world, then we could consider this a world model that we could query to get all the necessary data that we need to train a machine learning model. And so in this case, we'll have what I call here machine learning model 2.0, which is a recognition model or a representation learning model or any foundational model that you can think of. This model, as we know, is data hungry, and in this case has the ability to come up with queries through active learning, active acquisition to gather the data that it needs to train itself. And so it never stops learning and uses the acquired knowledge to decide what is useful to improve its own performance. And then on the other side, we have the world model. So in this case, I'll assume that it's a conditional generative model, a conditional image generative model for the purpose of the talk. And this world model provides an infinite data source that we can gather. So we can gather data from it. And so it can be queried by steering the model to generate the samples, the images that are useful to train the machine learning model, downstream machine learning model. Okay, and so as we were saying, in light of the recent progress in image generative models, we asked 2 questions, and we will go over these 2 questions. We'll start addressing these questions in this talk. The first one is are state-of-the-art image generative models optimized to work as world models? And so the assumptions here is that our model should yield high-quality images, and we probably all have seen how state-of-the-art models such as recent versions of Stable Diffusion, but also DALL-E and any model that you can think of seem to yield this high-quality image also when prompted with out-of-distribution prompts that are not very frequent in real-world data, such as an astronaut riding a horse. We also assume that these models should be consistent with the input conditioning. And what I mean by that is that we expect the generations to reflect what was requested through the user prompt. And we also expect the world models to be able to produce diverse samples. If we have a model that only produces like one single sample per concept, let's say, then it's going to be difficult to use this sample to train a machine learning model that generalizes to unseen things. And so what we see when we take a look at state-of-the-art generative models, image generative models, we see that they mostly optimize for user satisfaction. And user satisfaction seems to be defined more or less as a lot of quality in the image and also some degree of consistency. And this is what we see in the examples here. So if we prompt a recent state-of-the-art model with 2 dogs and a cat, we see that we do obtain high quality images. However, the number of animals does not necessarily match the ones that were requested by the user, although we do see dogs and cats. So it's like somewhat consistent with the user prompt, high quality images that are generated. However, if we start prompting the model with other prompts, such as a house in Europe, a house in Africa, or a house in South America, what we see here is that there is very little diversity and quite stereotypical images that we obtain. And so the second question that we will ask in this talk is, what's the most effective way to query or to control the generative model to produce samples that are useful to train our downstream machine learning model? And so let's start with the first part of the talk. So I'll be focusing on high quality, consistent, and diverse generations. And I'll briefly talk about a couple of contributions. So the first one is Begin. So it's an evaluation framework to evaluate geographic disparities in image generations. And the second project that I'll discuss is how do we improve the consistency, the input-output consistency of text-to-image models through prompt optimization. So Begin, quantifying geographic disparities. So in this work, we introduced 3 geographic indicators to measure potential disparities across state-of-the-art text-to-image models. And we started with a region indicator. So this indicator captures a measure of quality, and the proxy for quality will be precision here, and a proxy for diversity, which is coverage. You can think of coverage as a measure for recall. And essentially, this indicator tells us, provided a set of generated data and provided a reference data set that is representative of a region in the world, what's the proportion of images that are generated that fall within the manifold of the real data. So that would be a proxy for quality. So that's the precision metric. And for coverage, or similarly recall, it would be how well we can cover the real data manifold with the generated images. And what we observe here is that there are several different patterns that appear across different regions, but in general, there is a tendency for regions such as Africa or West Asia to either suffer in quality, so in precision, or in diversity, so in coverage. This suffer more in these regions than regions like Europe. Then we have like second indicator that is a zoom in version of the region indicator, where we zoom in and see what happens for particular objects in our data set and particular regions. Again, we observe the same patterns, and we have like a couple of examples here for the class car and cooking pot. So if we take a look at the generations for cars in Africa, we see that a lot of the times we have these these are like the generated, we have these sort of examples where we have like SUVs kind of vehicles and in desert-like or outdoors-like backgrounds. However, if we take a look at what we have in the data set, which would be the first two images here, those are more like sedan-like cars in cities. For Europe, however, this mismatch doesn't occur as often. The same for cooking pot. If we take a look at the generated images for cooking pot, we have a couple of samples here. We see that those appear rather rudimentary when prompting the model with cooking pot in Africa, which is not necessarily the case in the real data set. And this sort of bias does not appear when prompting the model for objects in Europe. We had a third indicator to measure the object consistency, so evaluating whether the object that was prompted for actually appears in the generated image. And again, what we see that a lot of the models focus more on the region part of the prompts, or in Africa or in Europe, and depict the concepts that they have learned from those regions, and in many cases completely disregard the object that was requested. So some of the results, so in this study, we evaluated more than 3 models. We evaluated 5 models, but I think like with these 3 models, we can capture well the main lessons learned from this study. So here I'm considering 3 versions of stable diffusion model. So the first one being V1.2, this appeared December 2021. A year later, we had stable diffusion 2.1. And then we have stable diffusion API, which we accessed in April 2023. So there is a year gap between the first 2 and half a year gap, more or less, between the latter 2. So what happens in image realism or quality, as defined with this reference data set of images? So we see that through time, the image quality keeps improving. So stable diffusion V1.5 has lower quality than the resulting images from the latest access to the stable diffusion API. However, we observe the opposite trend for image diversity and prompt image consistency. So I think like the overall finding here is that progress in image quality has come at the cost of image diversity and consistency. And so this puts into question the use of these state-of-the-art models as work models, as per our first slide. So if we wrap up this first contribution, we introduced 3 geodiversity indicators to measure the quality, the diversity, and the consistency of state-of-the-art text-to-image models, text-to-image generative models. We benchmarked 5 state-of-the-art models. So if you're interested in more results about all of these 5 models, I invite you to take a look at the paper. It's on arXiv. And our indicators highlighted that there are indeed disparities in real-world geographic representation. And notably, we observed that existing models often have less realism and less diversity of generations of objects when prompting with Africa and West Asia than when prompting with Europe. Prompting with geographic information, so car versus car in Africa or any region, comes at the cost of prompt consistency and diversity of the generated images for many of the models. And models exhibit more region-level disparities for some objects than for others. Of notable concern, what I have already mentioned, we see from all these 3 indicators that the progress in image quality has come at the cost of real-world geographic representation. So if we move on to the second project, and if there are questions, feel free to interrupt me at any point during the talk. So the second project that I'm gonna quickly go over is the project where we try to improve consistency via prompt optimization. And this is what we called OpT2I. So this project will try to leverage large language models in order to automatically come up with new prompts that are used to query the text-to-image model and yield higher input-output consistencies. So let's see an example of that. So we start with a user prompt, a raccoon wearing formal clothes, wearing a top hat, holding a cane. the raccoon is holding a garbage bag. It's an oil painting in the style of Vincent van Gogh. So we feed that to the pre-trained text-to-image model, and we get a bunch of generations. So we have a couple of them here. We see that the generations are, again, somewhat consistent with the input prompt. For example, we do not see the raccoon holding the garbage bag, but there is a raccoon with former clothes, etc. Then we want to capture these consistencies through a consistency score. So this is depicted as the scorer in the slide. And for the sake of an example, I'm considering like the scorer that is based on a VQA model that asks questions about elements that should appear in the image, and we get the answer. So is there a raccoon? Yes, but is there a garbage bag? The answer would be no. So we get an overall consistency score for this set of generations. Then we feed the user prompt and the scoring function.
Sorry, Adriana, I didn't get the scorer is an automatic process. It's done by machine learning.
Yeah, I will go over a couple of them later, but it's an automatic metric. In this case, it's an automatic metric that is called DSG, which is simply a metric that, given an image, produces a set of questions to which we know the answers to, and then we'll feed the generations to the model, like VQA model, essentially, and we'll get the answers for those questions. And so we get the user prompt and the result of the scoring function, and we feed that to a large language model. Then the large language model, so we'll do in-context learning, essentially, here. So we'll feed the large language model with a meta prompt explaining the problem to the large language model. And the problem will be that the large language model is an expert prompt writer, and it needs to reformulate the prompt, in this case, this prompt here, such that when the new prompt is fed to the text-to-image model, the resulting images are more aligned or are more consistent with this initial prompt. And we can repeat that as many times as we need, because by doing this iterative process, the large language model gets more context, because when we start, we only have one example, which comes from this prompt with the corresponding score. And as the large language model keeps trying new reformulations of the prompt, we are kind of building a data set of prompts and scores that the large language model can leverage in order to make a better guess of what would be a good prompt. So as a result of this iterative process, the large language model comes up with an optimized prompt. So this optimized prompt, if I read it, is a cultured raccoon wearing formal attire and a top hat, proudly holds a cane, while a nearby garbage bag is artistically included in the scene. The painting reflects the vibrant colors and textures of Vincent van Gogh oil paintings. And when using this optimized prompt and fed to the pre-trained text-to-image model, we have like a set of generations. In this case, we still have the raccoon, it's still like wearing formal clothes, and we do see that there is the garbage bag that appears. So in this ideal case, now the scoring function has moved from 66% to 100%. But well, it's not always the case that it goes to 100%, of course, but ideally what we want to see is that there is an improvement in consistency score by doing this automatic rewriting of the prompt. So let's take a look at some results. So I'll start with some results that we have on MS COCO dataset. So this is a dataset of real-world images with captions written by humans describing the scenes. And the first metric that we use, a score function, is decomposed clip score. So the clip score normally computes the cosine similarity in the clip embedding space between an image and the text prompt. However, there are like several studies that observe that up to a certain threshold, the clip score is informative, but beyond that threshold, it starts relying on like things are captured by the embedding. For example, if we're discussing the object car, beyond a certain threshold, it's going to be the understanding of clip of what makes a car more of a car than another car. So given that, and that we are dealing with sort of long sequences of long sentences, and this also has an impact on the value of the clip score, we decompose the clip score. And what I mean by that is that we take the prompt and we decompose the prompt into noun phrases. And then we compute the clip score between each of the noun phrases and the image, and we average the resulting clip score. So it's a bit of a clip score that indicates the object presence of these different objects in the scene. And here there are two plots. So we have the plot that in both x-axis are the iterations. Those are the LLM iterations to produce new prompts. And on the y-axis, we have the consistency improvement. Like the first one is when we consider the improvement of the generations on average, the one on the top considers if we take the maximum score that we get at each iteration. And overall, what we observe is that, well, we start with a drop, but this is perhaps to be expected in the sense that the LLM starts with a single example. It needs to explore a little bit the space of solutions before being able to produce new, better prompts. But with the iterations, like the results keep improving. Then we have three baselines here that appear: the blue, like the dashed lines, the blue, red, blue, green, and gray. Those are just simple paraphrases, so there is no feedback loop. So this is the baseline where we ask the LLM directly, given this user prompt, propose paraphrases of this user prompt, but there is no additional context that these prompts will be fed to a text-to-image model or any information about the scoring function. And the three lines that we see going upwards are different combinations. So it's the same process, but different combinations of large language model and text-to-image model. So we have examples for Llama 2, GPT 3.5 as language models, and LDM 2.1, this would be Stable Diffusion 2.1, and CDM-M, I think it's more commonly known as deployed method models. If we move forward, so same kind of plot. So now for party 2 data set. So party data set is a data set of prompts. In this case, however, the prompts do not correspond to real images. So we only have like a set of prompts, and they are usually sort of they do not describe real scenes. So it's more related to the example that I've shown before with the raccoon and the garbage bag and things like that. So this is results for party prompts. Again, using a scoring function, the decomposed clip score. So we see a similar pattern as before. So first there is a drop in performance, the LLM doing some exploration that then recovers. So we see that in this case, in particular, there are a couple of combinations. So the Llama 2 with Stable Diffusion and the Llama 2 with deploy. So Llama 2 is not, no, sorry, the GPT-3 with Stable Diffusion. So both of the models with Stable Diffusion have a hard time improving over the initial prompt, whereas for deployed, things go slightly better. So additional results. So now we go back to MS COCO dataset. We change the scoring function. So instead of the decomposed clip score, we are now using the DSG score. So this is the score that is composed of questions and answers about the presence of objects in the scene, and also about the relationship between different objects in the scene. And when we present the score to the model, we show both the questions and the answers, as well as the aggregated score. So this is a much more visually grounded kind of metric. So what we see on MS COCO is a similar trend as what we observed for MS COCO with the decomposed clip score, but there is still this upward trend. If we take a look at the maximum, we see that in this case, the improvement that we achieve is higher than when using the decomposed clip score. But again, this metric provides a lot more details and is more visually grounded than the decomposed clip score that we have. If we move to the same metric now on the party prompts P2 data set, again, we observe similar patterns. And I think what's noticeable here, if we compare the party prompt results with decomposed clip score and compare them with the party prompt results with DSG, there are like huge differences in the improvements achieved. So again, remember that party prompts is composed of these descriptions that are not corresponding to natural images. And these more detailed, so it's more complex kind of descriptions, and leveraging more detailed and visually grounded scoring functions helps boost the consistency, the final consistency by a larger margin. So we see the final results, and this is comparing paraphrasing with the OP-P2I method. With different scoring functions here, those are the objectives, so decomposed clip score or DSG, different LLMs, so Llama 2 and GPT 3.5, and different text-to-image models being Stable Diffusion and Deployed, and the two data sets. And we see that in all cases, we're able to improve like simple paraphrasing of the LLM. Now the natural question is like, okay, we're able to improve the consistency score, but are we paying any price? So what happens with the diversity and what happens with the quality of the images? So to assess that, we start by computing the FID score. So FID score is a proxy for image quality and diversity all together. So we compute FID score based on inception V3 features. This is IV3 as traditionally done, but we also computed using clip features. And this is the pattern that we observe. So in both cases, no matter if we use inception V3 or clip V3, we say that we stay within the same ballpark. So there is not a huge cost associated to increasing the consistency when compared to the FID scores. However, then we disentangle the FID into precision and recall, precision being a measure, a proxy measure for image quality, and recall being a proxy measure for diversity. And what we learn with these measurements is that by using our methodology to improve the input-output consistency, we are decreasing the precision. So we eventually obtain lower quality images, but lower quality images as defined by the reference data set that we have, and we increase diversity. This is perhaps to be expected given the exploration of the prompts that the LLM can perform that can go farther away from what is found in the reference data set. So some visual results. So we start with the initial prompt, 4 teacups surrounding a kettle with a corresponding score of consistency score of 0.5, and 4 generations, each one with its corresponding score. And then after that, I'm showing the result of the optimization process. So 4 teacups encircle a kettle, forming a cohesive and picturesque tea setup. And we see that the consistency has improved. Although the performance seems to be perfect, if we actually take a look at the pictures, it's not the case, but this is a limitation of the metrics that we are using that are not perfect. And this is another example. So this is the example of the raccoon. Again, just showing more examples. Initially, for example, where we see that again, in all of them, the garbage bag is missing, and it's a different style of painting than the one that I showed initially, I think. And we see that after reformulating the prompt, we find more of the elements that were not initially there. So to wrap up on this contribution, we introduced the first text-to-image optimization by prompting framework to improve prompt image consistency. We showed that this framework can be effectively applied to different combinations of large language models and text-to-image models, as well as different consistency scores, yielding improvements of up to over 20% in some of the cases. And the choice of consistency score is crucial, as we have seen, Complex prompts, such as the ones that we find in P2 in party prompts, appear to significantly benefit from more detailed scores, such as DSG, and as such, we expect that with the development of better metrics to capture consistency, eventually this kind of framework would be more successful. Qualitatively, what we observe in general is that the optimized prompts oftentimes translate into emphasizing the initially ignored elements in the generated images and also changing their position in the sentence. In many cases, we observe that the position is moved towards the beginning of the sentence, and this makes the text-to-image model more likely to generate the object itself. So with that, I'll close the first part of the talk, and we can move towards the second part. So that part will be about querying the generative model to produce samples that are useful for the machine learning downstream model. And I'll discuss one project that we had, which is currently a paper on arXiv. So if we go back to the initial slide, so we had the downstream machine learning model, the OR model. For the sake of this particular project, the machine learning model will be an image classification model, and the OR model will be a pre-trained text-to-image model. And the idea here is that the machine learning model, the classification model, will query the OR model, the text-to-image model, to produce samples that are useful to improve its downstream performance. And the OR model will generate the data that is requested by the machine learning model, the classification model. So what we introduce here is what we call feedback guidance for data synthesis. And so the idea is as follows. We start with an imbalanced data set. So you can think of any real world data set is usually characterized by the long tail. So some of the concepts are less represented than other concepts. So we start with this imbalanced data, and we use it to train a classifier. Now, this classifier oftentimes will perform worse on these concepts that it has seen less instances of. Now, we will use this classifier, and we will define criteria, several criteria, to guide the pre-trained text-to-image model to produce samples that are useful for the classifier. So the definition of this usefulness criteria can be thought of different ways. So we tried, it will only present results for one of them, but we tried 3 different criteria, one being the entropy of the classifier. So guiding the pre-trained text-to-image model to produce images that are high entropy for our initial classifier. But we also tried maximizing the error, so producing the images that maximize the error of the classifier, and also driving the diffusion model to sample images that are in the low density regions as defined by the classifier output. And the idea here is that because we're using a diffusion model as a pre-trained text-to-image model, and diffusion models are taking gradient steps to generate the images, we can complement the diffusion model sampling process with an additional term, which will be the derivative of the criteria. So in this case, the entropy, in order to produce the samples that are useful for the classifier. So we'll perform these steps, and we will get a set of synthetic data, which is here referred to as the SYN, and we'll put together the synthetic data and the real data in such a way that we obtain a balanced data set across all concepts. And then we will use these balanced data sets composed of real and synthetic data in order to train, again, our classifier, and hopefully this will help us improve the performance of the classifier. So we'll start with some visuals to understand what the feedback-guided synthesis can achieve. So here are some samples of real data sets for the Jack-O-Lantern class. Then we have the LDM generated data. So this is just the LDM prompted with the class itself. So no additional feedback from our classifier. And finally, we have some samples that are the result of using the feedback guidance. So for the LDM generated data, what we observe is that the backgrounds are very similar. The colors of the pumpkins are like white or orange. So there is overall little diversity in the generated images. If we take a look at the feedback guided generations, we see that the backgrounds are different, different numbers of pumpkins appear, colors are also more varied. So those are the kind of, so there is more diversity, but also this diversity is not any kind of diversity, but it's the kind of diversity that should be useful for the classifier. So let's see some results. So the table is divided in 3 different parts. So those are results in the ImageNet long tail dataset, which is a version of the ImageNet just made long tail to emulate real world scenarios. And so the first part of the table is methods that do not leverage any synthetic data. Synthetic data defined as coming from a generative model. Some of the methods do leverage some augmentations that we could also think of as synthetic data, such as mix-up, but it's a different kind of data. Then we have the methods that do leverage synthetic data. So there's a fill-up, which is the main competitor of this work, and then those two are baseline. So the LDM using a text prompt only, so no feedback guidance, and the LDM using text prompt and image as conditioning as well. And finally, we'll have the feedback guided results when leveraging the entropy criteria. And so we have results for like overall results in terms of accuracy, and also stratified results across different classes, many, medium, and few, which referred to initially the number of samples that we had for each class. For class few, sometimes we have as many as 5 real data samples. For many, it's usually higher than 200, if I remember correctly. But overall, what we observe is that we are able to improve upon previous results overall, but maybe more interestingly on class few, the classes few, which are the more challenging ones, usually the boost that we obtain with respect to previous methods, and in particular with respect to fill-up, is quite important, and a quite important boost of over 4%. Interestingly, if we take a look at the class few, so what we see is that, well, on the x-axis here, we have the number of synthetic samples used overall, and on the y-axis, we have the test accuracy on class few. So there are like some points there that correspond to some of the methods that do not leverage synthetic data as defined by a generative model. Yes?
Medium and few is the amount of data per class. Okay, and do you still increase, do you add synthetic data to the classes that are not really that many?
Yeah, yes, well, yes, but only not to all of the classes. So many, not all the classes in class many have the same number of examples. So they're
under the class that is the most of the.
Exactly. And here it's defined by the number of samples in the real data set. So when we do the union of the real data set and the synthetic data set, it's balanced, but these classes refer to the real data. Okay. So if we go back to the plot here, what's interesting to notice here is like how the performance evolves as we keep increasing more data points, so that we see that up to some point, adding more data points is not helping us. But if we compare the number of data points that we need to match the fill-up results, which are like the main competitor, the previous state-of-the-art in this data set, we see that we need essentially half or less of the data points that they actually need. So let's see more results. So those are results on Nico++. So this is, again, a data set that is characterized with a long tail data set. In this particular case, it's group-wise imbalance. So it's not a class imbalance, but we have class and setting. And this defines a group. For example, a fox in autumn. I think there's like R2 class and group that appears. And interestingly, for this data set, some of these group combinations have zero real sample. So in these two cases here, the blue ones, it's the kind of methods that do not use any synthetic data, synthetic defined as coming from a generative model. And the orange ones are the ones that are leveraging a generative model. So LDM would be, again, without the feedback guidance, the stable diffusion out of the box. The LDM with feedback guidance, it's what we propose, and it's, again, using the entropy criteria. And we see here that, once again, in terms of worst group accuracy, which is the way that the Nico++ is usually benchmarked, we can improve the overall results. And finally, we have like a third data set, which is places long tail. So again, a long tail version of the places data set, which contains indoors and outdoor scenes. Here, I'm depicting the accuracy only for classes few. Blue methods are the ones that do not leverage synthetic data as defined with the generative models. And the orange ones are fill-up and our LDM with feedback guidance. So again, if we compare the accuracy overall, we improve, but in particular, compared to the previous competitor, fill-up, we're able to boost the performance by almost 5 points. So if we wrap up this LDM with feedback guidance, here we studied the effect of leveraging the feedback from the classifier in order to generate data that is hopefully more useful for the classifier. So what we observed is that we are able to, by leveraging the feedback guidance, we're able to achieve the state of the art on ImageNet long tail with over 4% improvement on the underrepresented classes, while being twice as efficient in terms of the number of synthetic data points used. We achieved state of the art on the Nico++, again, with over 5% improvement in worst group accuracy. And the same for places long tail data set here with an improvement of 3.9% on the underrepresented classes. So our framework hopefully paves the road towards effectively leveraging high performance retrained state-of-the-art text-to-image models as data sources that can be queried to improve downstream models, downstream applications. And so I'll conclude the talk with some takeaways. So we started with the first question: are state-of-the-art image generative models optimized to work as word models? And as a reminder, we assumed that for these models to be useful as word models, they had to yield high quality data. The generation should exhibit representation diversity, and the generation should be consistent with the input prompt. So what we've seen in the projects that I presented, in the papers that I presented, is that progress in text-to-image models has been driven by image quality improvements, and the progress in image quality has come at the cost of representation diversity and prompt image consistency. What we've seen also is that consistency can be improved by leveraging high-performing large language models to optimize the prompts that are provided by the user. The second question that we asked is, what's the most effective way to query or control the generative model, the sampling procedure of the generative model to produce samples that are useful for machine learning downstream tasks? And what we've seen here is that leveraging feedback guidance from a pre-trained classifier to drive the generation process results in samples that are more likely to improve the performance of the downstream task. And we've also seen, I didn't show today the results, you can take a look on arXiv if you're interested, but different criteria yield notably different results. And so there should be further effort to devise these effective criteria for feedback guidance. With that, I'll conclude the talk, and I'll be happy to take any additional questions.
Thank you, Adriana, for your nice talk.
Yeah, thanks for the talk and sorry for being late. It's interesting work. I have several questions that will take maybe only two, just to give other people space for talking. I'm curious about your insights. Why the entropy is helping in that case? You know, when you generate new samples, because intuitively I would say that those samples are typically easy to classify, right? Because when you minimize the entropy, you push them away from the decision boundaries.
We're maximizing the entropy.
So you're not minimizing the entropy.
No, we're maximizing the
Okay.
entropy. Yeah.
Okay. That was my first question. I think that gives the answer. And second one is that how do you feel this can extend to segmentation problems? Because for classification, I think it's easier because you have the label, you have the image, you can just have this label as the output. But segmentation is way different. So how do you feel this could be extended for this?
Yeah, this is an interesting question, and like some conversation that we've been having with some collaborators. I don't think it's straightforward. I think the same kind of framework could be applied. Maybe the interesting question here would be also what kind of text, maybe not text image model in this case, but what kind of conditional generative model could be useful, and maybe going in this direction, it would give us more control if we thought of sort of layout to image generation. So you could control at least different regions what you expect to have, and maybe that could be more interesting. As for the criteria, I think I don't have a like straightforward answer for you, but I think it's definitely a really interesting question to think about.
Okay, thanks.
So I have a question. So first of all, thank you for the nice presentation. So to me, there is one danger of using this kind of pre-trained model for synthesis, creating synthetic images, like the leakage for the test set. So is there any study that's like I'm assuming that the stable diffusion has a large training data. Is there any study that there is no overlap between these benchmarks and the stable diffusion training data?
That's a good question, and that's true that there can be this problem. So for stable diffusion, the version that we use here is the unclip version, so it can be conditioned on both text and images. My assumption, this is to be checked, is that it was trained on the Lion dataset, and something to be checked is like what's the contamination of the Lion dataset. So this is something that we didn't check. I think there are papers doing this sort of analysis, and some of the datasets have reported to have some samples in there. I'm not sure if this is the case for the datasets that we have used, but it's a good point, and I think like the way there is like also like an easy way to check if you have access to both datasets to understand what's in there. But it's true that there is this risk. The generative models, yes, I mean, yeah, it's a text and image. It's usually scraped from the internet, so it's a bit noisy data, but it's annotated, yeah.
So what would stop someone from just taking that data and completing the data?
You could do that. You could use the real images to complete the data, but then there is like a question of like how do you select the image in not like you can still have like a criteria like the highest entropy or whatever, but you have to find like the images that do match the exact class labels that you have, and usually it may not be straightforward to do that from the perspective that usually it's a prompt that you have, and so the prompt can refer to the class in a different way, or I mean it's not like one-to-one kind of thing. And the problem with using the real data is that you lose the control of being able to steer it towards what could be more useful. I mean, you can still, among the data set that you have, do retrieval of what's the most useful, but the generative model should be able to also interpolate among all the data points that it has learned from. And so it's more steerable from the perspective of the usability, or it should be more steerable from this perspective.
You try to optimize the negative prompt with the library, you keep the same prompt, and then you have like you do like negative prompt on this same prompt to increase the diversity of the model.
so I'm trying to rephrase the question. So you're wondering if building negative prompts would increase the diversity of the generations, and you're wondering if this could be useful in which setting?
Oh, in the guide prompt, create more diversity for the.
So how are you thinking of creating negative prompts? Because usually for example, for vision language pre-training, for contrastive learning, you do that, but you do that by, for example, negating the sentence or like changing something. So I don't know if this is you have in mind, what you have in mind or something else, but then this could result in generations that are not what we are asking for.
In South America scenarios, we could like prompt things like it's exactly like this, but with some modifications on more buildings or things like that that would look not exactly like what we have.
Oh, so okay, but okay, there's maybe like a different point here. What you're suggesting is a way to potentially increase the diversity of the generated images. Those generated images may or may not be useful for a downstream task. I think like those are like two sort of separate problems. So what you're suggesting, I would categorize it more as a sort of a mitigation strategy to improve on diversity metrics, if we think of like the initial study that I have presented. Maybe this could be a way. I think like what we've seen like through like the second project of rewriting the prompts, you could also ask the LLM to provide you like with different prompts that could be more specific and then would fill the details of the image in different ways, and that can increase diversity in a similar way to what you're saying, which would be negative prompts, which, well, with the criteria that you should still ensure that the prompt that you're providing preserves like at least the objects or the region or whatever that you care about. So you don't want to alter this part, otherwise it would defeat the purpose, right? But this could be like some sort of a prompt engineering to increase diversity, and that could be a valid option, as long as you're mindful of what you can alter and what you cannot.
Oh, there is also a question online, maybe. Christian?
Yes, first I want to thank you for the very interesting talk. We're sort of trying to apply the same kind of concepts, but for domain generalization, which is a related problem, I guess. So I want to play the devil's advocate here and say that it seems to me that what you are doing is learning the class posterior, which is like P of y given x, by learning the class conditional generative model P of x given y. And to me, P of x given y is a much harder problem because, you know, the image space is so much bigger than the class space. So I want to know, like, from a kind of like theoretical point of view, how can this even work?
I mean, I understand the question that one modeling, like the generative modeling part is more difficult than the discriminative modeling part, but I guess I don't understand the question. Like, what's the alternative? So you're suggesting that it would be easier to just gather more
no, so
data, or like what would be the alternative that you're suggesting here, or like that you're questioning?
So what I'm questioning is that you're assuming that you have a really good generative model that, given a class, can generate images, right, that represent the distribution. But my question is, if you have this model, then you already have a discriminative model, right? You already know the distribution, so you should be able to discriminate properly the classes. So
yes, but this is again on like this is what you mentioned. It's under the assumption that the discriminative model is perfect and knows about all of the real world distribution. And but at the end of the day, what we care about is being able to improve on like specific data set, or specific task, which is not necessarily representative of the real world. And you need, so if you have the perfect generative model, I agree with you. My argument, I guess, is that we don't have access to the perfect generative model, and that even in the case that you do, you need to adapt this perfect generative model to produce the samples that are in the ideally in the distribution of the test that you want to test on. Of course, you will not use the test, but that's the ideal case, right?
Awesome, thanks. Yeah, but by the way, I was just playing the devil's advocate because yeah, we are, as I said, I'm exploring similar kind of ideas. So yeah, but thanks.
Thank you.
Thanks for your answer.
Okay, so thanks, Adriana, for the nice talk. Very well done. My question is about if you had to deal with, let's say, sensitive data. Let's say you had to deal with an application where there was a privacy concern. Let's say you're doing face recognition or something in effective computing. I'm just wondering, like, how could you adapt your model to make that work? Because it seems like you'd have to have just enough diversity so that you're generating, let's say, faces or other images that are just different enough from the real thing so that you see the question?
Yeah, I think this is a very interesting question. And actually, yeah, I've been reading quite a bit about these privacy concerns. And I think it's like a very important point that you're raising, especially because we've also seen that these diffusion models, like, or pre-trained anyways, whatever kind of generative models, are able to memorize samples. And so I think there's a higher risk involved here. Well, I think like the first thing, and this is more on the dataset side of work, I think it's important to get like user consent if you are going to use these generative models on in any way. That's like one thing. But even beyond that, if we don't want to like replicate the faces, I think like well, there is work doing that or suggesting these kind of ideas already. Maybe not like in the generative model space. Maybe yes, I'm not too sure about that. But it's more about being able to generate like this average kind of faces. This will at the same time reduce the diversity, of course, but maybe thinking like of different clusters and having like different average faces could mitigate a bit the concerns. I don't have like a more direct answer to that, other than I think this is like a very important problem to address.
Because even the amount of data, I imagine over time, it's going to be harder and harder to get personal data, right? And even data sets have disappeared because they're, I guess, when they got the initial consent, it didn't work, or the laws are changing.
Yes. Another way is like maybe there is a well, if we think of diffusion models because of the guidance, so we have like feedback guidance, but there might be another term that you can add to essentially move away from the modes that are more likely to contain these memorized samples. I mean, that it wouldn't be bulletproof, but maybe one step in this direction.
Thanks.
I have a question. I'm thinking overall, so you are proposing, or many people are proposing this kind of concept that instead of learning directly from images, you want to learn from these generative models that kind of summarize the data from the images. And I didn't think too much about this, but there can be some concerns about that. And one is about biases, in the sense that those models may amplify even biases that are on the data. And so do you have any recipe or anything that could try to avoid this kind of risk?
I think this is a great question. I think it's part of like the research questions that we're trying to address. I think like ideally we would like to get to the point where like these generative models that we're leveraging as world models do not contain biases, or we have mitigated these biases somehow, because what you're saying is true, and it's also what we see in the analysis that we have performed. Like we are currently working on mitigation strategies, and I think this is the part of, I think like both parts of the talk sort of connected in that, is that, well, if we want to have to be able to use generative model as world models, then we need to be able that at least we fulfill those properties, like the set of properties that we started with, of course, can be extended with like privacy concerns, like any other thing that comes along the way. But like the second part was more like, what can we do with what we currently have? But as for mitigations, we're currently exploring like the two words that I explained here that they can be applied for mitigation strategies. Like one, like the guidance part to increase representation, diversity, and the in-context learning part as well. In this case, it's more like rewriting the prompt into a set of prompts that will make your generations more diverse. Of course, this doesn't make the model less biased, but the output of the model is. I'm not saying this is like the solution, but it's like one step towards there. But I think there is a lot of work to do before we can actually use this or properly use these conditional generative models as world models.
Any other question?
Like when you are using this metric, right, the inception distance metric, like FID. So, like I understand it can be used to, understand the quality of the image, but how can that be used to say that the image which is created is diverse? Is it like you have some real diverse data to test the feature distance, or how does that happen?
So FID is a distributional metric, so it's comparing the distribution of real data with the distribution of generated data. So you will only be able to capture the diversity that is in the real data. And that's what you're using as proxy. And the same for the quality, right? It's the quality as defined by your real data set. So it's the diversity as defined by your real data set. So because it's comparing two distributions, it's just relying on the distribution. In this case, the diversity part is relying on the distribution on the diversity that can be found in the real data. But beyond that, it will not be able to capture it.
The interpolation can happen, but new sample, not like, even if let's say the model is able to generate that, but that FID metric might not be able to capture it. Like,
well, if it's very far away from the distribution, it can penalize for that.
Okay.
Because it's like, again, like we're grounding the metrics of quality and diversity to a reference data set.
Okay.
And for example, for quality is also a very subjective thing. So if you do user studies on image quality, the quality of the images is perceived very different. It's very subjective. It's perceived very differently by different users. It's perceived very differently by different cultures. What appears in a data set and that we use as reference to compute this proxy for quality might be very different. But well, maybe the other side of the coin here is that, well, these data sets are used to train some models. And if we're thinking of adding data points that are generated to complement this data set, it makes sense to consider like the diversity and quality as defined by this data set. So I think that this will be very much related to the use case that you want to use, whether FID is the proper metric or what, even if FID is, it has its own limitations, of course, but then what's the reference data set that you should be using? What's the feature extractor that you should be using? Because like FID traditionally relies on inception v3, but inception v3 embedding space is known not to correlate well in terms of like distance metric with human perception.
Thanks.
Any other question? Online? Yes, we should see that. Okay, so then thank you again, Adriana.
Thank you.